I have the pleasure of introducing Dr. Kumar Bijay Mishra. He's local, and this talk he'll be giving in person from this location. He works for U.S. Army Research Lab in Adelphi, Maryland. Dr. Mishra's talk will be dual-blind deconvolution perspective of integrated sensing and communication. So let me just briefly introduce. He is a real scholar. He works for Army Research Lab, and he obtained his PhD in electrical engineering and MS in mathematics from University of Iowa in 2015. He also MS in electrical engineering from Colorado State University. At that time, he was also working with NASA's Global Mission Ground Validation. He got his BTech from National Institute for Technology, Hamidpur, as a distinguished, I think he's a gold medal winner. He has been a prolific IEEE volunteer as well. I personally know him because he's involved in IEEE Future Network Initiative in the Massive MIMO working group. He's a distinguished lecturer for IEEE Communication Society, Aerospace, Electronic System Society, also IEEE Future Network Initiative. He has won many best paper awards. Can see that. He's been also elected member of 3 technical committees, IEEE SPS, SPCOM, and SPS. He has been also associate editor of many IEEE transaction aerospace electronic system. He got outstanding editor recognition award there. He has 3 books coming up, I guess. How do you get time to write 3 books? So you can hopefully see those available pretty soon. Signal processing for joint radar communication, IEEE Wiley, next generation cognitive radar systems. And the other one is advances in weather radar volumes. So with that, I'd like to invite Dr. Kumar Bijay Mishra to take the stage. Thank you. So Mitch, you can, yeah, right.
Okay, hello. Okay, good morning, good afternoon, good evening to all the people joining virtually, and good evening to everyone present here. Thank you very much to the ACM Baltimore chapter and Ashutosh for the invitation to present this recent research we have been doing at ARL. So I'm glad that Misha spoke before me, because he gave an excellent overview of some of the concepts that I'm going to cover in my talk. So he talked about the spectrum trap and the need for academicians and researchers to get into this solving the spectral congestion problem. Also, one of his slides was about use cases of 6G, and one of the use cases was distributed sensing and communications, which is exactly what I'm going to talk about now. He also spoke about need for higher data rates, bandwidth. So all of that actually very nicely connects to this talk, where I'm going to first give an overview of integrated sensing and communications and what it is all about, what is the current state of the art. And then we are going to look into this problem called dual blind deconvolution that we have been working on for previous year or so. And then we'll look into some other emerging trends in this technology. So I would like to acknowledge Dr. Brian Sedler, Professor Arguello, and his students, Edwin, Roman, and Jonathan, with whom I've been working on this problem, as well as funding from ARL and the National Academies of Sciences, Engineering, and Medicine. And since I'm speaking at APL, I could not have left out references to spectrum, radar, and communications from some of my favorite sci-fi, space-based TV shows and movies. So you will see some references which are pertinent to this talk in some of my slides. So for example, here from this Apple TV show For All Mankind, they have a scene here which is talking about interference from radiation to the Earth-based communication systems. And I'm going to talk about interference from radar to communications, communications to radar. So obviously, interference to communications and radar is not a new problem. It has been around for a while. In fact, some of the very early spectral coexistence papers can be traced back to as early as about 1960s. And then only recently it is becoming more difficult because of new applications. Otherwise, conventional radar systems or communication systems have dealt with interference at the receiver in one way or the other for decades. So currently, I would mention two most important applications that are driving research in integrated sensing and communication. So one of them is obviously trends in wireless communications. As you can see from a graphic here, it is expected that in the future we would have billions of devices that would be connected, and as a result the data traffic would also increase dramatically. There would be need to store and transmit exabytes of data in the near future. So with this increasing demand in this high quality wireless services like Misha mentioned, URLLC and several other applications, metaverse, we need a system to support these high data rates. So how do we do that? So we look into Shannon's capacity formula for some inspiration, and as you can see, this famous formula here, capacity is a function of the number of orthogonal resources n, which could be number of antennas or any other resources, maybe time slots and so on, bandwidth w, and then signal to interference plus noise ratio. So since SINR has a logarithmic relationship, you'll have to increase it a lot to gain this capacity. And then, yes, we do work with n, which is the number of orthogonal non-interfering resources. For example, you could adopt MIMO technology to increase the capacity. So number of antennas could be increased. But here specifically, we're concerned about the bandwidth W. Can we increase W? Now, obviously, it's a natural resource which is very scarcely available, and a lot of regulations exist on which bandwidth could be used for communications and radar. So there are already regulations there. And then it's not like spectrum is available and you can transmit everywhere. There are certain regions or frequencies in the spectrum where there is very high attenuation. So for example, in millimeter wave or sub-terahertz or low terahertz part region of the spectrum. And in that case, we have to exclude those high attenuation regions and focus only into transmitting within the atmospheric windows, which are regions of local minima in those regions of spectrum. So it is scarce. There are regulations. Not everything is useful. So we have to use bandwidth judiciously. And again, here is a connection with Misha's talk, because this lower graphic that you see here is what he had shown about for the future radio access. We could probably go to sub-terahertz. So this from Ericsson. So even though we would like to move to this higher end of the spectrum, millimeter wave or terahertz, it is still not sufficient to actually allocate spectrum for radar and communications, or radar or sensing applications and communications exclusively. Because the more we could utilize this, better we could serve the needs for wireless communications, that is high data rates for these various futuristic services. And radar's performance is also related with wider bandwidth, because wider the bandwidth, better is the resolution of radar, resolution being the capability of radar to discriminate between two very closely spaced targets. So radar also needs high bandwidth, but currently one of the applications that is driving the research in integrated sensing and communications, or ISAC, we sometimes also call it joint radar communications, or JRCM. There are many different terms that, as we'll see in a bit. In radar, it's autonomous vehicles, which are the use cases which are currently being investigated, where we definitely need some way to share the spectrum between communications and radar modalities. So if you look into some of the sensor-driven modern vehicles, where in some sense autonomy has been included in the system, then these vehicles, they typically consist, they have several sensors deployed on them. There's a GPS, LiDAR, cameras, ultrasonic sensors, radar, and so on. And these sensors are not just used to guide the vehicle in a congested traffic environment, but also to monitor the overall health of the car, for example, tire pressure and metrics like that, as well as to monitor the physiological behavior of the driver and passengers as well. For example, there are these in-cabin radars which could measure the heart rate or respiratory rate, or even drowsiness of the driver, which could be very helpful. And if we look into what are some primary sensors, then there is a high resolution camera, which can provide a very good visual of the surroundings, and it also has semantic information. There is a lot of metadata that could be useful. However, it doesn't perform very well when there's low visibility, either because of weather or because of poor lighting conditions, and it does not directly measure the Doppler velocity. It could infer the Doppler velocity of the vehicles by looking at the change within the frames, but there is no direct Doppler measurement. Then we have LiDAR, which has been a favorite of autonomous vehicle industry for a while, because it provides a very high range resolution, but it is expensive and it is usually mounted outside of the car frame. So for aesthetic reasons, some vendors may not prefer that. And as I said, it has a very high cost, but currently most of the industry statistics are such that they do not want these kind of sensors to cost more than $100 in mass production. So LiDAR is very expensive. So we come to radar, which is a cheap sensor. It can fit into that $100 bill in mass production. And it measures Doppler velocity directly because it's based on Doppler principle. There is no semantic information like camera, but it is very robust to low visibility conditions, because radar works both night and day. And in some cases, it can, even in a harsh weather, it can actually look beyond a distance that a camera would be able to visualize. So radar is important, and its performance, as I mentioned earlier, is directly linked to the bandwidth. The higher the bandwidth, a better resolution it can provide. Apart from this, a lot of modern cars, they are software managed, as you can see from another graphic from the industry that I've taken here. There are many functions because these radars are sometimes, the cars, they are sometimes fitted with very high processors. They're almost like a computer where a number of functions are monitored and managed through software. And they may also be connected. A car may be able to communicate with on-road infrastructure or with other vehicles, or even may have a satellite connection. So because of all these functionalities, these connected cars in the future as well, they are expected to generate huge data. And if we look into some of the industry statistics, it appears that current wireless technologies such as DSRC or CV2X, they are unable to support the kind of data rates that are expected from these futuristic autonomous vehicles. So, and as I mentioned earlier, to support these data rates, again, we need higher bandwidth. So these autonomous vehicles, they need higher bandwidth for both functionalities to stay connected for communications with infrastructure, other vehicles, or even some other, for example, base stations that may be dedicated for these purposes, and also to sense very accurately and give a good picture of the environment. So we need high bandwidth for all of these, and as we know, bandwidth is scarce. So shown here is a table of different IEEE radar bands, which are kind of already allocated for different applications. And as I mentioned earlier, the problem of interference or sharing of spectrum between communications and radar, that is not new. There has been some work in 1960s and even in 1970s, but it was really in 1980s when some of these radars which operate in VHF and UHF band, they started facing interference from TV or broadcast stations. And for example, foliage penetration radar used by military would usually have interference from some of these coexisting emitters. And the approach there was that they will just notch out the interference in the receiver, the result of which is there will be signal distortion, and because you're not using certain bandwidth, there will be loss of resolution as well. But in open radars, the bandwidth was so wide that you could actually notch out the interference without an appreciable degradation in the performance. However, with the advent of mobile communications as well as new applications of radars, for example, automotive radars, nowadays pretty much every IEEE band has some kind of communication services, either partially overlapping with the radar transmission or sometimes, for example, in millimeter wave band, when it is unlicensed, it is free run for any kind of emitter. So this has become a huge problem now. So DARPA, there have been several programs by governmental bodies to actually address this problem. So DARPA about 10 years ago had this program SSPARC, which was about spectral coexistence between S-band communications and S-band military radars. And later on, NSF and some of the programs were mentioned in the previous talk. NSF then had this year's program where they started investigating spectral interference across all bands. And then there have been several other iterations of those kind of programs like SWIFT, PAR, and so on. So, and nowadays, a lot of other societies, especially within IEEE, and including in ITU, people have become very cognizant of this problem. As a result, there has been an explosion of research in signal processing, communications, aerospace systems on how to address spectral congestion or spectral crowding or spectrum sharing between radar and communications. So broadly, two kinds of solutions have emerged. So this is a very broad picture. I'll go into some details in a bit. Depending on, so because we want to share the spectrum, one way is both radar and communications, they independently transmit or access the channel in the same spectrum, and then they have improved receiver processing technologies to mitigate the mutual interference from one to other. And in this case, the radar and the communications transmitter and receiver are separate, they are not shared. So this was something that was there in the early part of ISAC research, and we call this kind of paradigm as spectral coexistence. And if any one of either transmitter or receiver or both of them are shared, and in that case, there is probably a joint waveform that is being transmitted, then we consider it as spectral co-design. So spectral coexistence solutions were very good for legacy systems where we don't want to because of cost considerations, or we are unable to change the transmitter, receiver, or the hardware. In that case, we can do some kind of digital signal processing at the receiver for interference mitigation. But for the new systems that are coming up, we prefer spectral co-design where there's a common hardware, a common waveform, and there's a joint access of the channel. So obviously the more general version of this is subfigure D, where I give an example of a vehicular scenario where there is this red car, which is the transmitter for both communications and radar. So it sends a common waveform, a communications embedded radar waveform, for example. For example, it could be phase modulated continuous wave waveform. And then it goes towards the radar target of interest, which is the blue car. And from there, it gets scattered off and is received by the gray car, where the job of the gray car is not only to deduce the parameters of this blue car, which was the radar target, for example, its range, location, Doppler velocity, but as well as to decode the message, the communications message that was sent by the red car. So this kind of a bistatic co-designed system is more general. So I'd mentioned that vehicular applications are one of the major drivers of ISAC research, apart from many other applications nowadays. And this is an example from that kind of scenario. Obviously, this is a very broad categorization of ISAC, but in general, if we want to exhaustively see what other topologies exist, then you can classify them based on some of these metrics. For example, how radar and communications, they access the channel. Independent access, spectral coexistence. They may coordinate the access. Maybe radar and communication, they have some kind of information sharing between them, and radar accesses the spectrum for a certain time, followed by communications and so on, or what we call as opportunistic access of the spectrum. There may be a joint access, or there may be a shared access without actually any coordination of information between them. Then based on the hardware, we just saw whether it is the same or the common transmitter or hardware, based on the waveform. So you can take any kind of permutation and combination of different topologies listed there, and you'll get a new ISAC problem. And that's why when we look into ISAC literature, there are just so many variations of this problem depending on the applications. So a waveform could be separate, completely separate waveforms, a common waveform like communications embedded radar waveform, or there may be some kind of resource sharing in the waveform. For example, there may be a time slot, and certain time slots are used by radar, and then the rest of it is used by communications. Based on where these units are located, if they are co-located, that means at the same place, the transmitter and receiver. That is one configuration. And then we just saw the bistatic configuration. You can generalize it to multi-static or distributed or networked kind of system. And in that network, not all the nodes need to be identical. One could be phased array radar, another one could be a MIMO radar, or just a mechanically scanning radar. So it would be a heterogeneously networked environment. Then the performance or functionality. So you can have a radar-centric ISAC where the primary motive is to optimize the performance of radar, and communications is a secondary consideration, or it could be vice versa. And there we have joint radar communications where we do not prioritize one system over the other, but we are interested in the performance of optimal performance of both systems. And then we also hear this term dual function radar comms, where you have a transmitter or a base station that also performs the function of radar, but primarily it is a wireless communications node. And then we have different specializations like MIMO radar, MIMO communications could be combined, in-band full duplex ISAC. Intelligent surface could be a part of the channel, and that could be also, this is something that is of more current interest. There's been a lot of research in past 1 year or so on IRS-aided ISAC. And then we have different other specializations depending on frequencies like millimeter wave, terahertz. They all have their own separate set of considerations while designing ISAC. So there are a lot of activities going on within IEEE. ComSoc has ISAC Emerging Technology Initiative, where there's a lot of researchers have come together on addressing this challenge in various ways or the other. in RC, where Commission C is concerned with radar and communications, and I'm a vice chair of RC Commission C. There also we have some working groups looking into ISAC problems. Signal Processing Society has a technical working group dedicated to this. Aerospace and Electronic Systems Society also has a working group for ISAC. So it is a very interdisciplinary area. Multiple societies are involved in this. So obviously, this is something that is very difficult for me to cover in this roughly an hour-long talk. I typically do a 3 or 4 hour tutorial to go into all the details. So I decided I'll cover a problem that is very recent, and we are looking into that problem these days, which is the dual blind deconvolution. And another interesting facet of this problem was that originally I got this idea from an APL engineer. He's not with APL anymore, he works for MITRE, but I met him in a conference in 2016, and he was working on what he called as dual deconvolution. And we have done a variant of that problem by calling it dual blind deconvolution. I'll get into this in a bit. So this was the motivation on ISAC problem and how widespread it has become now, both in research and applications, and there's a lot of interest in industry as well, as you saw in Misha's talk. And then we get into this dual blind deconvolution to understand a very difficult version of this problem of ISAC. And then I'll follow it by some of the lead issues related with dual blind deconvolution. And then if we have time, I'll close it with some of the emerging trends in ISAC that we have been looking into. Okay, so in this problem, so this is, like I said, you can do a lot of permutations and combinations of various topologies that I showed, and you'll get a new ISAC problem because there's just so many different types of communications and radar systems available. So here we look into one specific case where it's a coexistence receiver, meaning the transmitters are separate for radar and communications. And there's a common receiver. The radar signal gets reflected off from the targets, for example, some aircraft, and then it is intercepted by this common receiver. Similarly, communications signal is also being transmitted, comes through various paths, and it is overlaid or superimposed with the radar signal at the common receiver. So in this case, normally in radar problems, we know the transmit signal, we don't know the target information, and at the receiver, the goal of signal processing is to extract target parameters. But there could be some cases, for example, passive radar, where we also do not know the transmit signal. So both the transmit signal as well as the radar channel, so to say, or radar target information is unknown. In communications, it's the reverse. In conventionally, you can estimate the channel, and the goal of the signal processing at the receiver is to decode the transmit message. So the transmit signal is unknown. But then as we move to millimeter wave or terahertz, where the channels are extremely dynamic, whatever estimate you may have may very soon become outdated because the coherence times are very short for those channels. So in that case, both the channel as well as the transmit signal may be unknown to the receiver. And then when they are overlaid, when they're superimposed, then you have these 4 variables that are unknown: radar's transmit signal, communications transmit signal, and their respective channels. So when all these 4 quantities are unknown, then how can we get information about both radar targets or communications messages? So obviously in each one of the problems, even though both variables are unknown, channel and transmitter, it is usually just one quantity that is really of interest. So in radar case, even though the transmit signal is unknown and somehow we would estimate it, but we are really interested in the channel information. And in communications, the reverse. We are really interested in the transmit signal information, even though the channel is also unknown. So this takes us to this dual blind deconvolution problem. So the very first equation that you see, if we look into a radar receiver, then it's the transmit signal that is convolved with the target profile or the radar channel, and then it is intercepted at the receiver. So there's a convolution of transmit signal and the channel, both for radar as well as for communications. And then when you superimpose them, then it is a summation. So if in a classical deconvolution problem, you will have a product, X and H, and you're observing it just through this convolved product, that is Y, and one of the components is unknown. So for example, H is unknown, X is known, and we would like to do this deconvolution to find out H. When you have the summation like this, and let's say in radar case, we know the transmit signal, that is X, and in communications case, we know the communications channel, that is HC, then it is, because one of the quantities is known in both cases, then it is dual deconvolution, which was this problem that Masoud Farsharshian, who worked for APL, that I came to know about this problem for him in a conference called Coursera, which was organized in Germany. And then with this ISAC problem coming up in the past few years, we decided to look into a more difficult variant of this problem where all four of these quantities are unknown. So that's why we are calling it dual blind deconvolution. Of course, you can have multiple emitters. There could be 3 radars and so on, and then it will become n-tuple blind deconvolution. I'll show it later that the solution that we propose could be generalized to even n-tuple case. We make some assumptions about so it's a ill-posed problem. That means if you don't have any additional information, you can, it's very difficult to solve. It's almost unsolvable. So it's ill-posed, which means that there could be multiple solutions that would map to the same YT. So we make some realistic assumptions about the problem. For example, the radar signal, we assume a pulse Doppler radar. So it is periodically transmitting a pulse train, and we can estimate its pulse repetition frequency, that is the interval or the periodicity of that signal. And there are ways to do a periodicity estimation. So let's assume we could estimate that. So we have the transmit signal, which is a pulse train. So we don't know S, for example, in this green box. And then we have a radar channel. That means there are, let's say, L number of targets. So it's a sparse scenario, which is also very common in radars. And each target is characterized by 3 unknown parameters. There is alpha r, which is the attenuation coefficient or reflectivity of the target, delay time or tau r, which is directly proportional to the range of the target with respect to the radar receiver, and Doppler velocity nu r. So these 3 parameters characterize every Lth target. And communication signal, we assume it is an OFDM signal. And the communications channel is also a delay Doppler channel, which is also common in some of these OFDM-related problems. So this long equation at the bottom that you see is when I substitute all these specific models in the dual blind deconvolution equation mentioned on top. And then there are all these unknown variables. All the channel parameters are unknown. That is, all 3 parameters of each target is unknown, and same with the communication paths. And we don't know the signals S and G as well. So very difficult, very challenging problem. So to approach the solution of this problem, and we'll take some of the assumptions into account. These are very realistic. For example, channels are sparse. That means there are just few targets. Obviously, there isn't a target at every arrangement, because if there is, you don't need a radar. You can actually see, for example, there will be aircraft all over in the sky, but there are just few aircraft. So channels are sparse. The channel parameters, they're continuous valued. So an aircraft does not fly at, let's say, 300 meters per second or 400 meters per second in quantums like that. Its velocity could be anywhere between, let's say, 100 meters per second to 300 meters per second. It could be 101.5 as well. So they are not discrete valued parameters. These are continuous valued parameters that complicates things additionally. For example, you cannot use simply DFT to actually find out, to look into, for the Doppler velocity in the spectrum, because in that case, you'll have to bin the spectrum, which means you're assuming that these are discrete valued. The transmit signals, we assume they lie in low dimensional subspace. So here there are certain representational bases that we could use. So S could be represented as BU, where B is a known matrix, and same with the communication signal. We assume this linear sensing model. So once you do this representation in low dimensional subspace, which is similar to lifting trick that is used in several ill-posed problems in signal processing literature, once you do that, then you can write the received signal as a linear model shown in this equation. The discrete signal model with the lifting trick can be written as follows. So Y is equal to Aleph R in terms of matrix ZR, and then plus Aleph C ZC. So ZR and ZC matrices, these are rank 1 matrices which have all these unknown variables encapsulated within their structure. And then as you look into the structure here, then we see there are these exponentials like e to the power minus j2 pi, which is all coming from taking a CTFT of this signal. So it's a frequency domain representation. So for the time being, if we can recover ZC and ZR, we have all these unknown variables within those matrices. So the way we solve this problem is, so as I mentioned, ZR and ZC, they are rank 1 matrices. We have sparse channels, we have continuous value channel parameters, and we want to do this super resolved estimation, that is very near perfect recovery of these unknown parameters. This is something that reminds us of atomic norm minimization problems. So people who are familiar with L1 norm, so L1 norm of a vector is the sum of absolute values of the elements of that vector. Atomic norm, you can think of it as a generalization of L1 norm. It is an analog of L1 norm, but for arbitrary basis. So if the bases are rank 1 matrices, atomic norm will be the sum of the absolute values of coefficients of those rank 1 matrix bases. So we do this representation in terms of atomic norm for the signal that you just saw, which was expressed as a linear model in terms of rank 1 matrices ZR and ZC. And then we cast this as an atomic norm minimization problem shown in the box here. So we are minimizing the sum of atomic norms ZR and ZC. So ZR subscript AR and ZC subscript AC, those are the atomic norms of ZR and ZC, and their sum, because we are observing the signal as a superposition. We minimize this subject to the observations Y. So all we have are just those observations Y, and these assumptions, that is sparsity and continuous valued parameters. So atomic norm minimization is great when you want to recover continuous valued parameters, which a DFT kind of tool will not be able to handle. So what we saw was a primal problem. That means minimize the sum given this constraint, but I cannot go into the computer and actually code that thing up. I need a semi-definite program which computers can solve, and how to arrive at the semi-definite program of this primal optimization problem, we need to look into its dual optimization problem. So there's a primal optimization problem, and you can cast it as dual, and sometimes the dual problem will give you some clues on how to solve the primal problem. And if you have equality constraints, so we had equality constraints in the primal problem, like Y is equal to the whole linear model. In that case, the solution of dual problem is exactly the solution of the primal problem as well. So we do this using optimization theory, go from primal problem to the dual problem, which is shown here. That is, if the primal was minimized, dual will be maximized. So you see the maximize Q, which is a dual variable, and then subjected to certain conditions on dual atomic norm. Even now, this is not something that I can program. It is not an SDP. So here there has been extremely beautiful work by several researchers, and there is a very nice book as well by Professor Bogdan Dumitrescu from Tampere University in Finland on positive trigonometric polynomials. So I had remarked about these exponentials that we saw in one of the slides. Those are trigonometric polynomials because you can express an exponential as sine and cosine. So when we have these, it turns out these dual atomic norm that you are seeing in the dual problem, they are positive trigonometric polynomial inequalities. And if we have these kind of inequalities, there is this very famous result in control theory that goes by bounded real lemma, where you can cast these positive trigonometric polynomial, we'll just call it PTP inequalities as a linear matrix inequality, which is this second last equation that you see. It looks very complicated, but once we get these LMI or linear matrix inequalities, this is an SDP that I can actually go into the computers and processors and can code it to get a solution of this dual blind deconvolution problems. So we get this semi-definite program, and now we can solve this problem using standard methods. So we have that solution, and then this whole solution that we saw, it is backed up by very strong mathematical guarantees. So it turns out once you get the variable q, which was the dual variable, it is a multivariable polynomial, and you plot it in a delay Doppler plane, that is one axis, it's a function of range and Doppler velocity. So if you plot it in this range time or delay Doppler plane, it shows peaks of, so it reaches its maximum modulus of unity is reached when there is a target present at that range and at that Doppler. So that is what this guarantee says. And then it also mentions what is the minimum number of pulses you should intercept and minimum number of samples you should get, which is like, so M and then P are the number of pulses. What should be the minimum number so that there is a near perfect recovery? So once we plot this, as you see, this is how the dual variable looks, and wherever it assumes the value of unity, its modulus, that's where you can localize the targets in the delay Doppler plane. And we did these experiments for closely spaced targets and then randomly spaced targets. There are multiple variations of these experiments that we did. You can find the details in the paper here. So this is broadly the framework of how to solve this very difficult dual blind deconvolution using theories of positive trigonometric polynomials. So the beauty of this problem is it comes from an actual application, but the tools that are used to solve it, they are taken from optimization theory, from functional analysis and control theory, all of that coming together to actually solve a very applied problem. So this was a very simple model. I mean, if it already looks so complex, let's look into relaxing some of the assumptions that we made. So we look into some of the practical issues. So for example, so far we assumed that there was a synchronized transmission of, in the first version of this problem, we assumed that both radar transmitter and communications transmitter, they transmitted at the same time. However, this may not be the case in practice. There may be some delay between their transmissions. So if there is this lag between them, so here I'm mentioning in the graphic that is shown on my right side, the unsynchronized transmission, where there is a lag of tau e between the communications transmission and the radar transmission. So how can we apply the same theory now? So first we'll obviously have to estimate tau e. There are some ways in the literature when you can estimate this lag and then you correct for that lag and then solve this problem, the dual blind deconvolution. The method that we suggest is that we would estimate tau e jointly with this estimation of unknown parameters together. So we cast the problem in this way, where this matrix E is a diagonal matrix that encapsulates this lag. So there's a difference between one of the properties of this lag is it is going to be the same between different pulses that you capture. So if it is going to be the same between the different pulses, while the targets may be moving, then that is a property you can utilize or exploit to address this problem, and then proceed with the SDP formulation using theories from positive trigonometric polynomials. So we show here how that formulation will look like and can be solved using similar methods that I mentioned earlier. Then there could be multiple limiters like n-tuple blind deconvolution. So in that case, you will have as many linear matrix inequalities as the number of emitters you have. So if you have 5 radar emitters, 6 communication, then you are going to see 11 linear matrix inequalities in the SDP formulation. So it's very easily extendable to multiple emitters. So far we considered a noiseless scenario. Obviously there is going to be noise. So if there is noise in the received signal and you could estimate its variance, that is, we know that what its variance is through maybe previous measurements. In that case, you can take that into account as a penalty function in the optimization problem as shown in the SDP on the right here. Another interesting version is what happens when there are multiple antennas. This was just one antenna, but if we have a phased array receiver, and in that case, then the problem would become you have to estimate the range, the Doppler velocity, and now the angle, the direction of arrival as well. So we show that it's possible to incorporate this additional unknown parameter in the problem and then solve it using very similar theories. So in that case, our dual blind deconvolution model would look like this. So I'll just focus on the equation at the bottom where you see this parameter beta R and beta C, which are the DOA or direction of arrival parameters, which are also unknown apart from everything else that was unknown in the first version of this problem. And then we are here using NR antennas in the receivers. So when you have these additional parameters, at the same time, you also have now multi-channel measurements that you can exploit to actually solve this problem and estimate beta R and beta C. So we have very similar guarantees here. Again, the guarantee for recovery is that you look for the maximum modulus of unity while plotting the dual polynomial, and wherever it is unity in this now 3-dimensional version, in this hyperplane of beta R, that is direction of arrival, delay or range, and then Doppler velocity. So in that 3-dimensional plane, you have to find out this maximum modulus of unity, and wherever it is, that gives you the location of the targets. And similarly, we have the guarantee for how many minimum number of pulses, range samples, and receiver antennas you need to do a perfect recovery. And another practical issue could be there could be errors in the steering vectors. So if there is an error in the steering vector of the array, and there could be error in both gain and phase, you can actually take that into account in this formulation and then modify your atomic norm minimization accordingly. So far we have seen it's possible to extend this DBD problem to multiple antenna cases, multiple emitters, presence of noise, lack of synchronized transmission, and errors in steering vector. So it's fairly generalized to different practical scenarios. And there are more scenarios that we discuss in our paper. You can refer to that for details. So this is the steering vector error. Now the primal takes this form with 2 penalty functions, and then dual you formulate in a very similar way using theories of PTP. So it's very difficult to show this 3-dimensional plane in a graph like this. So what we have done here, we have shown it by keeping one variable constant and then plotted it for delay and Doppler by taking different values of DOA, and then we show that wherever it reaches the maximum modulus of unity, that's where you actually get the location of the targets. This was a framework where we refer to atomic norm minimization. So by no means that is the only tool to solve this problem. There are many other ways, and sometimes they give us deeper insights into the problem. So for example, one of the conditions for the recovery of parameters in the atomic norm minimization based method was that the targets, they should have certain minimum separation between them. And similarly, there should be certain minimum separation between the communication delays. And those, even though it's a joint problem and we are doing joint recovery, with atomic norm minimization, we could only guarantee this separation for radar and communications separately. But we were interested in, could we guarantee just one separation for communications to communications delays, radar to radar, and radar to communications? And in search of that kind of recovery guarantee, we started looking into Berling-Selberg extremization theory. So Berling was a Swedish mathematician, and while working on this problem, I came across this very interesting anecdote from his career. We were looking for good references of Berling's papers while writing this paper, and we were unable to find any. And then I read in Berling's biography published by American Mathematical Society that he rarely wrote any papers, but he gave a lot of talks, and his colleagues later on compiled the ideas from those talks in 2-volume books. So that's why this concept actually comes from that compilation of his talks, but it is very well known in the signal processing community, people who are familiar with these kind of problems. So the concept here is as follows. So here we are, this is something that we have just started looking into. So I don't have this generalized dual deconvolution problem that I discussed so far in atomic norm minimization framework. Here we are looking in a very similar problem, a very simpler problem, where the radar and communications channels, they only have the reflectivity and delays. So no Doppler and no DOAs. And then we have this version of the DBD problem that is shown at the bottom after taking the CTFT of the received signal. So no Doppler, no DOA. Can we recover this? So we know from atomic norm minimization, indeed we can do this recovery, because atomic norm could do recovery of a much complicated problem. But now we want to solve this using Berling-Selberg major theory, and we want to come at this joint separation guarantee. So the way we address this is, you can write, because you have all these exponentials, you can write this in the form of Vandermonde matrices, one for radar, one for communications, and collect all your unknowns in this vector called phi. So then I rewrite my overlaid receiver signal in terms of this Vandermonde matrix and multiplied by these unknown parameters. So in order to find out the stability of this problem in the presence of noise, can we guarantee the recovery? We need to look into the condition number of this combined Vandermonde matrix VG. So we have this theorem where we say that just this delta, which is a joint minimum separation, either between radar, comms, or radar, comms delays, the condition number depends only on that joint separation. So if this kind of condition is satisfied, if delta, the separation is given by this condition, then we can perfectly, there is noise stability of this problem. So Berling-Selberg extremization, what it says is, so you saw this VG phi. So the received signal could be written in terms of Vandermonde, this generalized Vandermonde matrix VG, and then unknown parameters phi. So VG phi. So I expand it, and then I look at the norm of that received signal. It turns out that when we have these exponentials, then Berling-Selberg theory tells us that there are these functions that we call as Berling-Selberg majorant and minorant functions, which can bound these kind of functions on both sides. So if we can bound this, then the condition number is actually the max divided by the min. And if I have bounds for both numerator and denominator, in that case, I know this condition could be satisfied, the one that I showed in the previous slide. So this is an interesting result, because normally when you are working with atomic norm minimization, the goal is to look at the problem jointly for radar and communication. So even though we are doing a recovery jointly, the guarantee for recovery was separate. Now, this kind of theory actually allows for this joint guarantee. So that's what is the takeaway of this problem. And then for recovery, we use a different method, low rank Hankel matrix recovery, which is actually standard in the blind deconvolution literature. You can actually extend this to dual blind deconvolution problem as well. And then we have these numerical experiments where we show that this Berling-Selberg based approach, where we are using low rank Hankel matrix recovery, that can actually outperform atomic norm minimization. Now, of course, we have not yet generalized this second approach to DBD problem for Doppler velocities, DOA, and all those generalizations that I've shown you earlier. But at least in the delay-only case, this method gives better results than atomic norm minimization. Finally, I wanted to mention, so obviously I can't miss Battlestar Galactica, which is the favorite space shows for many of us. Finally, I want to mention some other ISAC related problems that we have been working on. Some of the interesting ones. There are many others that I've left out from here, but you're welcome to catch me in a tutorial in radar conference or any other conferences that I usually attend. I mention those tutorials in my LinkedIn feed, so you can follow the tutorial announcements there. But there are a few other trends. For example, there are sensor fusion based approaches that are of interest, especially in automotive integrated sensing and communications, where radar and communications, they may have a common receivers, but the processing is done separately for radar and communications. And later on, using theories from sensor fusion, like Dempster-Schaeffer theory, you could actually combine the results to get an improved detection performance for radar. And I have provided the references here from our papers where we have looked into some of these. Misha had talked about privacy and secrecy. So we have the secrecy rate problems as well in DFRC, where you have an eavesdropper. So obviously when you're combining sensing and communications, radar is opening itself up to communications, and communications messages may also be intercepted by some other hostile entities. So if you have an eavesdropper present and you're doing this joint communication and sensing transmission, then how to minimize the transmission in the direction of eavesdropper? Those are the kind of problems that people have also looked into in secrecy rate for DFRC. Passive ISAC or distributed ISAC that I had alluded to in one of my slides. There's a lot of work in that area as well. These days, novel architectures are being looked into for terahertz, low terahertz joint radar communications. For example, how to manage this huge number of antennas at those frequencies that Misha had talked about. So you could employ hybrid beamforming. But then how to do that for both joint radar, both radar and communications is a problem that people are investigating. And a very recent development for past 1 or 2 years is use of intelligent reflecting surfaces for ISAC problems. You can use IRS, it's like a passive surface. You can mount it on the walls or on top of buildings, and all it does is the reflection, and sometimes it can do a few more functionalities. And if you have such a device mounted on walls and buildings, then how we can incorporate it for communications and radar separately as well as jointly is a problem that has generated a lot of interest in recent times. We are organizing an ISAC workshop in the 2023, the flagship conference of Signal Processing Society, which is ICASP. This year it will be held in Greece, and we have ISAC workshop there. And if anyone of you is interested in submitting your high quality papers, then the deadline is actually very close. But if you want an extension, please reach out to me and we can work something out. So please submit your papers here. And even if you're not submitting and want to attend, there will be a lot of keynote addresses by leaders in this area, and as well as panel discussions on the future of ISAC, so that may be of interest. We also have a special issue that I am co-editing with some of the colleagues of IEEE Journal of Selected Topics on Signal Processing, which is about use of machine learning for ISAC-based processing. And the manuscripts are due by May 15th, so I invite all of you to send your entries to this special issue. Finally, here is, I'm plugging my book here, upcoming book here, on signal processing for joint radar communications, to be published by Wiley and IEEE Press jointly. It should be out in a couple of months. It's almost ready with some proofreading going on. And with that, I would like to thank you for the invitation as well as listening to my talk. And I'm here for any questions that you may have. Thank you.
Sir, how does the performance of this sensor get affected in the presence of other RF interference?
Yes, of course. So, I mean, communications is one of the interference that we are dealing with here. So by sensor, I am assuming a radar or similar, say even a passive sensor. So one of the problems that is almost immediately you can see in a radar or a radar sensor performance is the loss of resolution. Because when you have interference, then the usable bandwidth, because if there is a particular frequency at which interference is encountered, that frequency becomes not very usable in the receiver. And as a result, there is a loss of bandwidth. Loss of bandwidth leads to loss of range resolution as well as signal distortion. So that is something that is immediately clear, and then everything else carries forward in the processing chain. For example, your tracking would be degraded, detection, estimation, performance as well.
A question from the floor, Ashutosh here. Excellent talk. I know you have a little bit of theory and practice. What you talked about reconfigurable intelligent surface, right? I think previous slide. That's a very interesting thing now. Do you have any bottlenecks there in terms of what is the challenge that needs to be solved? Have you looked into that?
There are many challenges, and I would love to come for another talk just on that, reconfigurable intelligent services. But just to summarize what we are currently experiencing is, so when you have, so you can use this intelligent surfaces in two broad ways. One, it could be a part of the channel. That means it is not co-located with the transmitter or receiver. So suppose I mounted it on the wall for indoor communications or sensing, or it is on top of buildings or other infrastructure. So it's part of the channel in that case. And there its job is primarily as a reflector. So the transmitter sends a signal, goes to the target, comes back via the intelligent surface. And this is very useful for non-line of sight sensing and communication. So when the direct path to the target is not available, then the sensing can be done using these reflector surfaces. Same with communications. You can extend the coverage. You can also use it to cancel the interference sometimes and so on. The main challenge here is that the signal that you get in the non-line of sight case, that is very weak. So it's far weaker than the direct path, and then to extract useful information from there becomes very difficult. Similarly, this is just one surface, but in practice we'll have multiple such surfaces, and then there may be cross interference as well, right? So those are, and there are many other challenges that I would love to go into detail in a separate talk. And then there are implementation challenges. So there have been some implementations recently. So for example, NTT Docomo in Japan have actually demonstrated outdoor communications using metasurfaces. And then there are several startups. Greener Wave is one of them. There have been some experiments at university level as well, what they call as smart walls. Huawei has been funding a lot of research in this area as well, especially in Europe. The second way you can use this is where it is not a part of the channel, but exactly at the transmitter. And when that happens, primary purpose over there is that if you use a normal phased array, you have the antenna, you have a lot of back-end digital as well as analog circuitry. if you use the surface at the transmitter, you can actually include some of the analog components within the surface. So what we call as programmable metasurface-based arrays. And that kind of research has been there for a while in the electromagnetics and antennas communities. Now it's just trickling down to signal processing and communications more recently. And there are several challenges. For example, apart from implementation, near field communication. So in near field, you don't have a plane wave front, you may have a spherical wave front, and then you get this range dependent beam pattern from where you want to extract useful information and so on.
I guess, what do you see the biggest challenges for the implementations of these solutions for these ISAC problems?
Yeah, so I mean, obviously, from theory to practice, there's a lot of things lost in translation, right? Then you become more humble as you start implementing some of these solutions. That said, there has been work on prototyping, and various research groups, people have demonstrated spectral coexistence, for example, that is relatively easier. But even joint radar communications, you'll find some groups. So, for example, ComSoc's ETI on ISAC, the Emerging Technology Initiative on ISAC, has a separate committee which looks into this prototyping work. And if you go on the website, you'll see like a list of prototypes that are available. From there to industry, as Misha mentioned, that we need more academics and researchers to look into this problem, how to turn it into something that is more usable. I would say that work is ongoing. People are very, very actively looking into these solutions. A lot of companies are interested into this. Nokia, Ericsson, Qualcomm, Huawei, all of them at some level are looking into this.
Do you see this as like a main bottleneck for getting to fully autonomous vehicles? Is this one of those main bottlenecks?
Well, autonomy has a lot of bottlenecks because we still do not have a fully autonomous vehicles running on the roads. Of course, there are trials going on, as you would have read in the news. This is one of the bottlenecks and a major one, but not the only bottleneck for autonomous vehicles. I want to be careful there because you can have an autonomous vehicle without this intervehicular communication, just a radar based, which can impart some autonomy. But yes, to achieve full autonomy where the vehicle is fully connected, this is something that needs to be solved. But there are so many things, right? I mean, better AI is needed for autonomy, which we did not cover at all in this talk. So one of the major bottlenecks, I won't say it's the only one.